On with the real stuff. So,
Our test is next Thursday, right?
right. It's not this week. It's a week from Thursday. Yeah, it's a week from Thursday. I haven't decided. Thursday we'll have lab, and I've got two options, so I don't know which one to go with. I like them both. So, we'll see. So, a couple topics still to cover after we talked about stoichiometric calculations. Remember stoichiometric calculations, if you have to give a definition of stoichiometry, it's basically you have the mass of something, usually the mass, could be moles, but you have the amount of something and you need to find the amount of something else. That's a stoichiometric calculation. It could be, a pair of reactants, It could be a reactant and a product. It could be two products, okay? But you're going from the amount of something to the amount of something else. Now, a theoretical yield problem is a special type of stoichiometric calculation. So if I put an R here, hopefully you guys know that's reactants. Goes to form P for products, right? So a theoretical yield is a special type of stoichiometric calculation in which you are given, or you know, the mass of your reactant, and you are going to calculate the mass of a product. Okay, it could be mass or moles. Okay, but this is a theoretical yield calculation. Okay, it's just a special type of stoichiometric calculation. Stoich calc. And we spent some time, and your homework should reflect that time that we spent talking about how you would do this. Of course, you would start out with the mass of what? R for the reactant. You go to the moles of R. Okay, using the molar mass of R. Okay, the flipped version, right? And then you go to moles of product, moles of P, okay, and then you go to mass of P using its molar mass, mm of P. Okay, the flipped version. Okay, so theoretical yields you guys have been doing. It's just a special type of stoichiometric calculation. So theoretical yields are a stoichiometric calculation based on amount of a R reactant. How much product should you get back in theory? And I think I mentioned this the other day that usually what you think you should get back, you don't get back. And it's usually because you're usually biased low. Usually you never get what you think you should get. It's kind of like life. You usually think you should get more and you don't get quite that much. So usually they're biased low. And all of these reasons I'm going to show you are biased low. With that in mind, though, you guys' copper experiment last Thursday, good job, by the way, for not blowing up the lab or anybody getting severely burned. Thank you very much.
By acid.
I know, by acid. Okay. But did you guys notice that your copper looked kind of different? It didn't look like that shiny. And honestly, that's an example of if you were to weigh it back, you had more than 0.50 grams afterwards. Some of it was water because we didn't dry it, but some of it mostly was impurity. But usually it's biased low. So these are actually 5 reasons, or several reasons, why you should get low yield, okay? We're going to call it actual yield, your experimental yield, your actual yield, what you usually get will be less than theoretical. And one is reaction kinetics, and I like that. Basically, reactions don't happen just like that. And so this is my impatient thing. So if your reaction really takes an hour and you don't give it an hour, your yields are going to be low, right? Another one's kind of fun, and I'm actually going to take a little bit and look at each one of these reasons for not getting your what you think you should get back. Equilibrium are awesome because basically they go back and forth. We're used to reading just a one-way reaction arrow. So we're used to, it starts with reactants and goes to form products. But if your reaction is in equilibrium, it also goes from products back to reactants again. Okay, so you'll see actually 2 arrows. And if that's the case, you're never going to you're never going to take the reactants and entirely convert them to products. Another one actually ran into with your magnesium oxide when you guys burned them. You were after magnesium oxide, but an unwanted side reaction was actually magnesium nitride. And I think that was in the background information. So that just means if you get magnesium nitride instead of the oxide you were after, your yields are going to be low. It's an example of an unwanted side reaction. And the other one, the last one in here, I guess there's only 4, is physical losses. Now I'm going to show you the oops error, and physical losses is not oops. Physical losses, what I say, and I'll use the word inherent. I just like the word. Physical losses are inherent. I don't know if I'm spelling that right. Inherent to experimental design. I like the term experimental design. Okay, it just means that because of how you're running your experiment, you're going to lose some. Sometimes it's like in transferring from reaction containers. I have a slide here that basically says you can count on physical losses if you're trying to purify something. You kind of lose a little bit. Pharmaceuticals are all about pure chemicals, and they lose a lot. That's why they're so expensive. So just taking a look at each one of these. Reaction kinetics, I said, are the basically you don't give it enough time. Okay? And so I have an example here. So for instance, and we'll use the RP convention. The reactants are there in red. You can see time is actually along the x-axis. And so the reactants, the red, decrease over time. The green are the products increase over time. So this example here is, what if you were to be, I guess you call it impatient. What if you say, I only have time to allow this thing to go on for 7 seconds? So what you do is, let's see, that's 7 seconds right here. That's on the time. Okay, you go up here, and at 7 seconds, okay, notice that you still have some of your red. Okay, the amount of red you have left over is about half. Okay, the amount of green you have formed is about half. Okay, if you were to squelch the reaction at that point, you're running about 50% of what you were trying to get. Okay, so this just says, you know, if you're too much of a hurry, okay, you're not going to get your entire, actually this kind of looks like it just did. How long would you have to allow it? 30 seconds? Well, no more than 30 seconds, right? Reaction kinetics. That's basically a study of how fast things happen. All right. So the second one was equilibrium. I said a lot of things actually go back and forth. If you enjoy learning about acidities and basicities, you know, the hydrogen ion concentration in water, that actually is a back and forth. That's a chemical equilibrium. We are only now getting to that in general chemistry too. So an example of a chemical equilibrium would be this one, where you have H2 and I2 in equilibrium to form 2HI. Is a balanced equation? Yep. Okay. So this is to say, can you see where at a certain time, and I'm not sure I'm going to pick that right time. Again, time is along the x-axis, but at a certain time, basically our concentrations of HI and our concentrations of I2 and H2 level out. So equilibrium are awesome. Okay, they basically reach what we call equilibrium concentrations. Are you going to get all product? No, HI, because it goes back to form H2I2. And it's dynamic. It's like not the same molecules stay what they are. They're dynamically going back and forth, but they are in equilibrium concentration. Okay, so again, you wouldn't get 100%. This was the one with the magnesium reacting with oxygen to form magnesium oxide versus magnesium reacting with nitrogen in the air to form magnesium nitride, the unwanted side reaction. Okay, and then the last one, this is not the oops. I'm going to introduce a term called gross error. Okay, gross errors are not inherent to your experimental design. Gross errors, just like the word gross says, it's the crap. Okay, gross errors was, oh, I didn't mean to do that sort of thing. Okay, physical losses are acceptable to say that it's a way of getting low yields. Okay, so this is my thing about pharmaceuticals. Especially if you're going to be ingesting something, you basically need to make sure it's pure. There's different ways of purifying a substance. That's actually a really kind of a cool study of chemistry. But every time you purify it, you lose a little bit of it. So it's kind of fun. Organic chemistry, kind of grr about that. Okay, so Theoretical yields are stoichiometric calculations based on a mass of an ingredient, mass of a reactant. How much product should you get? That's your theoretical yield. So theoretical yields then, on a practical standpoint, you'll only get it if all of we're going to talk about limited supply reactants here in a minute, but only if all of the thing that you have on a short chain run is completely reacted, okay? If there's no side reactions, okay? And if you're able to go ahead and capture that product in your experiment. So, a lot of experimental designs will try to optimize all of this. Okay, it's a little game that we play. Okay, so gross error then is the oops error. Okay, so this is oops, and you can fill in your own expletive. Oops, there we go. Oops. And does it happen? Yes. Do you call it for what it is? Gross error? Yes. I would say it's inherent to the experimental design. Okay. So inherent to the experimental design is basically if you know that you have to take your stuff and transfer it to another beaker or reaction flask. You just know that because that's your experimental design. You're going to lose a little bit. But a gross error would be if you literally spilled some of your stuff. A gross error would be, and have consequences, if you misread your scales. Okay. A gross error would be if you do your calculations incorrectly. Okay. A gross error would be if you're following somebody's experimental procedure and you don't follow it correctly. Those are gross errors. And hopefully your consequences will only be that your yields are low. No missing limbs or... So actually this part of your lecture, you can imagine on your unit exam, you're going to see some questions. I don't know if they'll be fill in the blank questions or kind of a short answer question, but I'm going to ask you questions about this in the lab setting. Is it lunchtime yet? I'm ready. Dang. Okay. So, there's kind of a simple, actually it's simple, the ones that are going to be due for Wednesday. They're pretty straightforward problems. There's a problem called percent yield problem. And if we do one of the labs that I have in mind for Thursday, you'll be doing some percent yield problems. But it's kind of intuitive. Percent yield basically says what you actually got in the lab, okay, divided by what you thought you should have gotten. Okay? So actual yield, sometimes we'll call that experimental yield. Actual is experimental. What you actually got. And this theoretical yield, actually that comes from stoichiometric calculations. And we already said there's a whole bunch of reasons why, not just gross errors, there's a whole bunch of reasons why your experimental yield or your actual yield is going to be less than your theoretical yield. Notice that it could be grams that you thought you should get, or sorry, grams that you got versus grams you thought you should get. Okay, it could also be moles that you got versus divided by moles of a product that you thought you should get. So we'll do an example here. The thing to focus on when you read it a few times, since this is a yield problem, is it says we did a stoichiometric calculation before that says based upon 1.25 grams of Cl2, you should theoretically get 1.61 grams of PCl3. Okay, we did that before. That's your theoretical yield. See, a theoretical yield is just a stoichiometric calculation. And then they go on to say they did that where it's 1.25 grams of Cl2, sufficient P4. We'll talk about why we say sufficient. But the mass that we actually got back was 1.08 grams, which it's lower, right? You thought you should get 1.61, you got 1.08 grams. So the percent yield would look like this, where basically we take that 1.08 grams that we got, divided by 1.61 grams that we thought we should get from the stoichiometric calculation. And then we multiply it by 100% to get it in parts per 100. So your percent yield is 67.1%. So they're pretty straightforward. So let's take a look at these calculations. It's kind of the standard. Make sure that you show all your work, include all of your units. Okay, but these are, I say they're straightforward, but I guess everybody's a little different. Looks like this. Okay, where they're 59 and 60, and it's just like that PCL3 problem, where notice in the green I've asterisked the actual yield, and the red I've asterisked the theoretical yield for both of these problems. So 59, if the theoretical yield of something is 24.8 grams, and what they got back was 18.5 grams, what's the percent yield? Okay, a division problem will get you there. Don't forget to show your work. And 60 is similar. It doesn't say what the chemical reaction is, but it says the theoretical yield using stoichiometric calculation, we thought we should get 0.118 grams, but what we actually got, again, was low, 0.104 grams. Now, is it possible to get, so these will both be less than 100%, right? Is it possible to get more than 100% yield? Yes. Like with your copper black, you would have gotten more than 100% yield, even if you dried that stuff. Inherent to the experimental design. Okay, oops. All right. So the last topic I want to cover here, actually there is no more assignment slides in this part. Well, there is for Unit 4, but not in this part, Part 2. I want to talk about another type of calculation. The calculations we've been doing are stoichiometric calculations. They are simple stoichiometric calculations. The other type of stoichiometric calculation, you can imagine, must not be simple, right? It's actually called limited reactant stoichiometric calculations. But I want you, and not to say that I wouldn't ask you a question like this on the test. Basically, in this sort of problem, it deals with the reactants, limited reactant stoichiometry, and it basically says that you are given amounts of multiple reactants, and before you do your calculation, you have to find out which one you're going to run out of first. The one you're going to run out of first is your limited supply reactant. Okay? So what I did was to go ahead and bring in that Browning's recipe. All right? So let's just say I'm going to put some have amounts, okay, next to the ingredients. I'll put it in green. Okay, let's just say, with regard to eggs, let's say you have 9 eggs. Okay, let's say you have 4 cups of sugar. Let's see, what else do you want to say? Let's say you have 4 cups of flour. And let's just focus on those ingredients. Okay, 9 eggs, 4 cups of sugar, 4 cups of flour. And someone says, you have an army coming over to your house soon, and you are supposed to make as many brownies, make as many batches of brownies as possible. Using this recipe. And just eyeballing it, do you see where if we went with, well, let's focus on the flour. Okay, so I need a ½ cup for each batch, and I've got 4 cups, so I could have 8 batches, right? 8 batches. That would be cool. That would be an army. Moving up, do you see where if those are have amounts. I have 4 cups of sugar, so I could make 4 batches. So already I better not be making 8 batches because I can only make 4 batches, right? But if we go up to the eggs, if each batch needs 4 eggs, and I have 9 eggs, I can only make 2 batches, right? So those ingredients are like your reactants. Can you see where I can't go with 8, I can't go with 4, I have to go with 2. So the most number of batches I can make is 2 batches. And as I've done this, actually this is what we call the eggs are in limited amount. Limited supply. That's your limited supply ingredient or limited supply reactant. That's exactly how that works. And now I'm even more hungry. So I have a similar example to kind of show you with, instead of making brownies, we're making sandwiches. And of course, if you're making kind of your typical sandwich with 2 slices of bread and 1 slice of ham, we kind of have coefficients of 2, 1, and 1. 2 pieces of bread plus 1 piece of ham will make 1 sandwich. So let's just say you go to your cupboard, and it's just very similar to the brownie exercise. If I make, if I write down my have amounts, I have 20 slices of bread and 7 slices of ham. Let's see. Looks like if I go with the bread, I can make 10 sandwiches. And if I go with the ham, I can only make 7 sandwiches, right? So do you see where it looks like our ham is our limited amount again? Just because of that. It's limited, why? Because we're going to run out of it first. The other thing that's very important about your limited reactant, whether it's eggs or whether it's ham, is it forces how much product you can make. In this case, the product is the sandwich. In the case of the brownies, the product is the brownies. We could only make 2 batches of brownies based upon our eggs. Okay? We can only make 7 sandwiches based on our ham. Okay, so that's it's a limited amount. I call it your short chain. I say it basically sets the tone for the amounts that's going to be reacted. So let's scale it up and look at something different. This is the Haber process does this quite well. It makes liquid ammonia or gaseous ammonia. Gaseous ammonia, I guess. So this is balanced with 1, 3, and 2 stoichiometric coefficients. And if I say up here your have amounts, with regard to nitrogen, we're going with 6 molecules. And with regard to hydrogen, we're going with 12. Okay. Notice that the relationship between nitrogen is a 1 to 2. The relationship between hydrogen is a 3 to 2. So does this make sense? It looks like I could get, let's see, 1 or 2. It looks like I would get 12. I could get 12 NH3 units with my N2, and it looks like I could, well, let's just see the video. I'd have to do it I'd have to show you how to do it. So now I'm going to show you that the only thing is on the front end, you need to look at all your reactant amounts and see which one you're going to run out of first before you do your stoichiometric calculation that you've been doing. Okay, but I will count on you understanding this concept. Okay. So I'm holding you accountable for the simple or ordinary, okay, stoichiometric calculations. We've run into those in this part already. So for instance, when we did the calculation with the Cl2, okay, reacting with the P4, it said with regard to P4 there was sufficient amount. You had extra left over. Okay, that clearly would tell you that your limited reactant was Cl2. Then we did our stoichiometric calculations. Okay. Very good. Well, I do want to go start the next part on solutions. I think it's the right thing to do. Okay. We won't, I don't think, get to an assignment slide. We might. So, like, I've got the screensaver where it's supposed to be like water, and to me that always sounds like a monkey. Like, what does monkeys have to do with water? There it is. All right. So, in your lab last Thursday, you guys dealt with 3 acids. Like I said, you did fine with those 3 acids. But those acids were described in terms of a capital M, the molarity of those acids. And so this is actually where we're going to start to talk about how were those acids described in terms of how concentrated they were. That's the big M, that's the molarity. So this actually deals with solutions. And I brought this, I don't know if you guys necessarily have this in your notes, but you probably recognize it, that matter can either be a pure substance or can be a mixture. And then we said, if you focus on the mixtures, we said that actually it could be the same throughout or it could be chunky. Homogeneous means it's the same throughout. So honestly, do you buy this, that solutions are actually a type of homogeneous mixture? We've got some terms coming up, a lot of S's. And solutions are great in that basically, I kind of show them, this is my beaker, okay? Solutions we generally think of, we are adding what's called the solute, and we are dissolving it in what's called the solvent, okay? And the solute plus the solvent is equal to the solution. Okay, so the whole thing is the solution. Lots of S's. But it doesn't have to be a solid added to liquid. It doesn't have to be a liquid added to liquid. It doesn't, I'll just kind of show you the possibilities. But the thing about mixtures, if you remember pure substances or mixtures, they're just tossed together. No covalent bonds, no new substances, they're just tossed together. So the cool thing about mixtures is they can be separated back out into their components. So that's the deal. We're going to be dealing a lot where the solvent is actually water. So those are called aqueous solutions. So an example of a solution is in this room. Okay. So we're running about 80-20 nitrogen oxygen. Can you separate them out? Yes. You know, they're not bonded together or anything like that. Are they homogeneous? Probably. Okay. We can actually have a gas dissolved as the solute in a liquid. So if you have any soda pop, okay, carbonated beverages, your carbon dioxide gas is dissolved in sugar water, basically. Liquid to liquid, how do you like that example? I'm not much of a drinker, but vodka actually is a mixture of ethanol and water. The most common one is basically where you have a liquid solvent, okay, and you dump some sort of solid in there, okay, solid solute. Like if you make up a sugar water solution, if you make up a salt water solution, okay, that's probably the most common. Then, and I think this is exciting, we have our solid to solid solution. Like, how does that work? Well, actually, you make them in their liquid stage. You take an assortment of metals that you want to make your stainless steel, liquefy them, mix them up, make them homogeneous, let them solidify, okay? And then you have a homogeneous solution of solid particles. Those metal particles have not formed any new bonds. They're just hanging out. So that's a good place to stop. So we'll pick up here on Wednesday.